We'll now look at neutralization, and specifically the acid-base reaction. Many biology students study what happens when an egg is placed into the weak acid vinegar. The acid is acetic acid. You may recall, the eggshell dissolves in, that is, reacts with the vinegar, and that's an acid-base reaction. As Arrhenius saw them, we can look at acids and bases and give a definition. Arrhenius looked at neutralization as the reaction of an acid and a base to form water and a salt. So HA, which is a general form of an acid, reacts with MOH, which is how he saw bases as hydroxides, to form HOH, water, and the resulting salt is the cation of the base and the anion of the acid. For example, hydrobromic acid will react with rubidium hydroxide to form water and rubidium bromide. Nitric acid would react with magnesium hydroxide to form two waters and magnesium nitrate. Notice that this requires two nitric acid units for every magnesium hydroxide because there are two hydroxides and a magnesium hydroxide unit. The net ionic equation can also be written, and it's the same for both. The business end of the acid is the hydrogen ion in aqueous solution. The business end of the base is the hydroxide ion, and they react to form liquid water. The hydrogen ion from the Arrhenius acid reacts with the hydroxide ion from the Arrhenius base. Let's look at some practical applications of neutralization. Sodium hydrogen carbonate is actually the emergency chemical used in the lab if we spill an acid. That's a base, and it neutralizes hydrochloric or sulfuric or nitric acid if we should accidentally spill it. Magnesium hydroxide, known as milk of magnesia, it comes in a blue bottle, can relieve indigestion by increasing the pH of stomach acid. This chemical, or magnesium citrate, is sometimes used as a purgative. Anhydrous ammonia, gas, is used in acid soils to raise the pH and add nitrogen. However, you must not use it in a basic soil because it makes things worse. And ammonia is really not the greatest fertilizer because it can deplete the soil of important nutrients and organisms. Acid-base reactions invite stoichiometric quantization because 1 mole of hydrogen ions reacts with 1 mole of hydroxide ions to form 1 mole of water. Very predictable. We say 1 mole of acid equivalent reacts with 1 mole of base equivalent. We say also 0.01 moles of acid equivalent react with 0.01 moles of base equivalent, or 22 millimoles of acid equivalent react with 22 millimoles of base equivalent. It's always a 1-to-1 ratio in the stoichiometry. Now, let's introduce a concept called normality. It's a way to level the playing field between, say, HCl, which is monoprotic, and H2SO4, which is diprotic. An equivalent is the number of moles that produces 1 mole of hydrogen ions, or 1 mole of hydroxide ions. Normality then becomes the number of equivalents of acid or base in a liter of solution, whereas molarity is the number of moles of acid or base in a liter of solution. For example, 1 mole of hydriodic acid has 1 equivalent. 0.5 moles of this sulfurous acid has 1 equivalent because sulfurous acid is diprotic. It kicks off 2 moles of protons for every mole, and therefore half a mole of sulfurous acid will kick off 2 times 0.5 or 1 mole of hydrogen ions. So how many moles of magnesium hydroxide would have 1 equivalent? Answer, 0.5 moles, very much like the sulfurous acid on the other side. Now we measure acids by volume. You may have done that already in order to get a certain number of moles or millimoles of acid into a container. At the neutralization point, we call that the equivalence point, not exactly the same as the end point. At the equivalence point of an acid-base titration, the equivalents of acid are equal to the equivalents of base. We've added just enough base or acid to neutralize all the equivalents of acid or base present at the beginning. But equivalence of acid equals the volume of the acid times the normality of the acid. And equivalence of base equal the volume of the base times the normality of the base. So at the end point, the volume of acid times the normality of the acid is equal to the volume of the base times the normality of the base. That's now our new definition of the equivalence point. How do we know the equivalence point? Well, generally, we use it from the end point. And the end point is, if we're doing a pH titration, we see an abrupt change in the pH, several pH points after one drop, or the change in color of an indicator when one drop of excess acid or base is added. The indicator that we've added to the acid or base changes colors. So, for example, we may ask how many milliliters of 0.2 molar HCl react with 45 milliliters of 0.15 molar NaOH. And for any of these problems, of course, you can just stop the video, try to do it yourself, and then come back and check your work. Equivalence of acid equal equivalence of base. Both acid and base are singlets, HCl, NaOH, so molarity and normality are the same. We have our VA-Na equals VB-NB. We are looking for the volume of the acid, so we're going to multiply the volume and normality of the base and divide by the normality of the acid. When we do that, we put 45 milliliters as the volume of the base from here, 0.15 normal as the molarity and normality of the base, and then we have 0.2 normal or molar for the acid as our divisor. When we do that, we get 33 milliliters, two significant digits because our molarities / normalities were of 2 sig digs, and now we've got a sensible answer. The base is weaker than the acid, so we should need less acid than we do base. A new example. 32 milliliters of what molarity HCl will react with 40 milliliters of 0.15 molar NH4OH. I recommend you turn off the video and then come back and check your work. Equivalents of acid and base are equal. They're both singlets, so the molarity and normality are the same. VA-Na equals VB-NB. We're looking for normality of the acid, so we multiply the volume of the base and normality of the base together, divide by the volume of the acid. We put the numbers in units in, and we end up with 0.19 normal or 0.19 molar, two significant digits. And this is sensible that since we need less acid than base, so the acid must be more concentrated than the base. Here's another example you may want to do and then check your work. What volume of 1.5 molar calcium hydroxide reacts with 32 liters of 6 molar HCl? This looks like more of an industrial than a laboratory application. We have our equivalents of acid and base are the same. For calcium hydroxide, the normality is twice the molarity. See, CaOH taken twice. So it's 1.5 molar, but 3.0 normal in the hydroxide. We introduce our equation. We solve for the volume of the base. We plug in our numbers in units, and we get 64 liters as our answer, two significant digits, and it's sensible. Calcium hydroxide is about half as strong in hydroxide as the acid is in hydrogen ions. One more and you may want again to turn it off and check your work afterwards. And this will conclude this part of the slides. What volume of 0.32 molar sodium hydroxide would react with 5.6 milliliters of 0.25 molar hydrochloric acid? We have our equivalents of acid and base are equal at the equivalence point. Normality and molarity are the same for sodium hydroxide, 0.32 normal. We have our equation. We solve for the volume of the base, which is what we're looking for. We plug in our numbers in units, and we get 4.4 milliliters. And again, the sodium hydroxide is about 1.4 times stronger in hydroxide than the acid is in hydrogen ions. Therefore, we're going to need less of the base than of the acid. Our next slides, we will go into how we do a titration.